During last years, we've seen lots of new systems, such as MapReduce, Dryad, Spark. All these systems are trying to always process over increasing amounts of data. And when you look at how they represent the computation, they usually have distributed data flow graphs, which make easier to make them, to provide high parallelism to run on clusters, but then you, of course, need to worry about fault tolerance, how to make them fault tolerant. And that means that when you program these systems, you really need to learn new ways of writing these distributed flows. So in this work, we make state explicit in the data flow programs so that you can represent, you can have mutable state in your programs, which means that you can write a Java simple imperative style code that will run at scale. So let me go over this example of a recommender system, which is an algorithm that requires this concept of mutable state. So this is a program where we want to recommend items to users in a similar fashion as Amazon or Netflix do today. And for that, this program has a user item matrix, which will keep all those ratings per user for the different items in the system. And it will also have a concurrence matrix where the intuition is that it will keep the number of times that two items have been rated together. So the general intuition of the algorithm is that to provide a recommendation, we will get a user vector from the user item matrix, and by multiplying it by the concurrence, we get a resulting vector where those items that have a higher value are those that we most likely want to recommend. Then to run this algorithm, we will have an add rating function, which will first update the user item matrix whenever there is a new rating. And it will also update concurrence to always have latest data there. And of course, we have a get recommendation function, which will execute this multiplication that I was saying, where we pick the user vector, we multiply by the concurrence, and we get the recommender vector. So because we've used explicit mutable state, we can represent that algorithm in a very concise way, but these representations also complicates parallelism and it complicates fault tolerance. So when you think about it and you want to run this on large data, most likely is that you will need to run it on distributed nodes, which means that you need to, well, worry about failures. So if there's a failure in a machine, you cannot lose the state, because otherwise it would mean that you will output wrong results. And it also complicates parallelism, because if, well, to make this parallel, you need to handle that state somehow, because now it's distributed across different machines. So before going into the details of how we propose a solution for this problem, let me go over how current distributed data platforms solve this issue. So they, as I was saying at the beginning, represent their computation as a data flow graph, such as that picture there, where the nodes are doing computation and the arrows are the data that goes across them. So when you think of MapReduce, for example, there's no explicit state. There is no state in the data flows, which means that everything has to be represented as input data and output data of map and reduce task in that case. When you look at Spark, for example, they have richer abstractions to provide more powerful ways of processing data, but they don't have mutable state either. So the issue here is that, of course, this lack of mutable state is very good for fault tolerance. It facilitates fault tolerance, but it also requires new programming models. And the challenge is that many users of these big data platforms, they don't really have the skills to understand those new programming models and to rewrite all their algorithms. So hence, the goal of our work, which is we want to run Java programs that have mutable state, but with the performance and the fault tolerance of current big data platforms. And to do that, we introduce stateful data flow graphs. So this is a new data flow abstraction where we introduce mutable distributed state explicitly in the data flow graphs. We provide some annotations that will help us to translate the Java programs to stateful, to this new abstraction. And we also have a checkpoint-based fault tolerance model that helps us to recover the state even when this is explicit and after a failure. So this is the outline of the talk, where I will start first explaining stateful data flow graphs and the distributed mutable state abstractions that we've introduced. Then I will go to the translation process, so how we go from the Java program to the stateful data flow graph. I will then explain the checkpoint-based fault tolerance model that we propose, and we'll end up with the experimental evaluation. So the main insight about stateful data flow graphs is that they now explicitly separate data from code and state. So the main idea of this is that by having all these individual units, it's going to be easier to then parallelize them as required. So when you look at the picture, stateful data flow graph is formed by task elements, which are the circles. And now it also has this explicit state, which are those red squares there. And then when you want to execute one of these in a cluster, what we do is we materialize those task elements to physical nodes where they run there for low latency. And for high throughput, we want each of those task elements to always access state locally. So what this means is that when we want to increase high throughput and we want to scale out those task elements, because we want to keep that local state to that local access to the state, we need to handle that state somehow. We need to parallelize it. And it is for that reason that we introduce this distributed mutable state abstraction, of which we have two types. We have a partition mutable state abstraction, which is used by those task elements that always access the state by key. And when that is not possible, we have a partial state element abstraction, which is used when you want to access the whole state. So a bit more detail about this is, in the case of the partition state elements, what happens is that we split the original state element into disjoint partitions. So if the original one was handling a given key space, the different partitions will now be handling a disjoint sets of those. So to route data in this case, what we do is we hash the incoming data so that we can choose dynamically to which particular text element to send the data. So when you think about the online recommender system that I was explaining at the beginning, this is, for example, the abstraction that you want to use for user item matrix, where you could partition that matrix by row, which then would mean that each of the different parallel task elements will be handling a different subset of the users. So for cases where you don't want to partition the state, we have partial state elements. What happens here is that the system will give a node, each node in the system a local state instance. This means that each task element will be updated independently their own partial instance. And here there is an additional decision that we have to make, which is whether we want to access only one of the running partial instances or if we want to access all of them. That's what we call local access in the case of one and global access when we want to access all of them. And here there is another thing that we have to put attention, which is what happens if you are accessing to all of the instances and you are reading some data. So if you do that, you will get partial results at the output, which is probably not what you want in your algorithm. What you want is to perform some kind of merge logic, which is application specific, so that you get your own result. So stateful data flow graphs provide a mechanism in this case, which is a barrier, which will collect these partial results, provide it to the merging logic so that you can then output your result. So I'll go next to explain how the translation process works. And this consists of two stages. So in the first one, we do static code analysis so that we can go from the Java program to the stateful data flow graph. In the second one, we do bytecode engineering so that we can adapt that stateful data flow graph to run on SIP. And SIP is the prototype that we've implemented to run SDGs on top and to run our fault tolerance mechanism. So more details about these two stages are here. In the first one, we statically analyze that Java program. And what we do is we detect the state and the state accesses. So the idea is that by having this information, the state accesses, we can then split the code into the different task elements, basically having all the pieces that we need. There is also the data flows for which we perform a live variable analysis so that we can understand what's the actual data that has to be streamed across the different task elements. The output of this first stage is the stateful data flow graph, which is the input of the second stage, where we use the connectivity information that we already have in this stateful data flow graph so that we can then understand what are the changes that we need to do to the code, what's the new method calls that we need to introduce so that it is compatible with SIP. So another thing to note here is that, well, there's some additional details that we cannot automatically know from statically analyzing that code, which is, For example, what is the actual distributed mutable state abstraction that the user requires? We've said that this is something that is application specific, so we don't have that information, and then we need some way of disambiguating that type of state. For that, we introduce a set of annotations, and I explain those next. So we have a partition annotation which annotates a Java field in the program, indicating that that particular field is partition state. Once we have this, we perform static code analysis on the code, detecting all the state accesses, so that we can automatically know what's the partitioning strategy for that particular state. So we have also a partial annotation for the cases where the state is partial. Again, this annotates the Java field. And in this case, I said that we need to also make the additional decision of whether we want to access only one instance or more, or all of them. So if we don't do anything, the default case would be to access only one. And for accessing all of them, we provide a global annotation that when it's annotating the state variable, it will trigger an access to all of the instances. So here we have a case where we are accessing all of the instances and we are actually reading data. So for that case, we said that we need some merging logic so that we can reconcile that data into one single value. When the user requires this, we provide that collection annotation that will trigger this mechanism in the stateful data flow graph, put in the barrier and put in the new task element that will then execute the merging logic. So by annotating the input parameter of a function and writing the specific way, the application specific way of merging those results, we get this result, this output. So next I will explain how on this model we provide fault tolerance. So when you're running the stateful data flow graph in the cluster, those task elements are materialized in physical nodes, and they are accessing local state from the memory. So the issue here is that, well, if there is a failure and you lose that state, results will be grown, and so forth. We want to avoid that. To do that, we first checkpoint the state, and then we back up the state. And here we have two additional challenges. So while checkpointing, we cannot mutate the state, but we also don't want to stop the data processing path because it will have an impact on the throughput. And for the backup, the problem is that we don't want to keep it in memory to reduce the resources of the cluster, but if we write it to a single disk, it will be slow. So what we do is, in the first case, to do the checkpoint, we just freeze the mutable state by keeping all updates to that state in a dirty state structure. Then, when the checkpoint is done, we reconcile that dirty state with our state, and this is actually the only point where we need to really log the access to that state. And for the backup problem, we follow, or we inspired from the mechanism that RAM clouds use, which is, instead of trying to send your data to a single node, we first split that state, we stream it to distributed nodes, harnessing parallel disk writes, and actually we use this same mechanism if there is a failure. So if one of the machines fail, to recover it, the distributed chunks first split their state, and they recover in parallel to n nodes. So by using this M2N distributed backup model, we are basically speeding up both the backupping mechanism and the recovery time. So for evaluating stateful data flow graphs, we wanted to answer three questions. We wanted to know how does mutable state impact the performance of the system. We wanted to know how efficient are the translated stateful data flow graphs, and we also wanted to understand a bit more about what's the throughput and the latency trade-off when compared with other systems. So in this first experiment, we run the online recommender system, where in the x-axis we change the add rating and get recommendation ratio. So that's writes and reads to that state. And what we see is more or less constant throughput, but the important result that I want to highlight is the fact that all the results that this algorithm provides are fresh and are within half a second in the median of the latencies. So this fresh means that basically we are providing results that already incorporate the latest data. And that is in contrast with other systems where you perform the concurrence in an offline system and then you have to move the output to a serving layer. So basically you are providing those recommendations on stale data. So the outcome of this experiment is that with stateful data flow graphs, we combine batch and online processing to serve fresh results even when operating on large mutable state. The next experiment, we wanted to understand how efficient is the stateful data flow graph representation, and for that we run a batch-oriented iterative logistic regression algorithm, and we report the results for Spark and stateful data flow graphs. So the results here show that SDGs are slightly faster. The main reason is probably due to the scheduling overhead in Spark, because in contrast, in SDGs, all the tasks are always living. So the outcome for this experiment is that the translated representation that we get achieves a performance which is similar to non-mutable data flow systems. Last experiment, we wanted to know the latency throughput trade-off, and for this we run several systems. So in this first graph, the important result is that systems such as SDGs and NIAD configured for low latency, that's small batches, achieve the same throughput overall the experiment. So this experiment is basically reporting counters over a given wall clock window, which then means that if we change that window in the x-axis, the smaller it is, the lower latency we require. So what we see is that in this case, the throughput is always constant. So this is in contrast with systems such as Streaming Spark or NIAD when it's configured for high throughput, where the throughput goes down once the requirements for low latency are smaller. The outcome of this experiment is that then with stateful data flow graphs, we can achieve high throughput while even maintaining low latency. So in this work, we run Java programs with the performance of current distributed data frameworks. We wanted to do that, and we introduced stateful data flow graphs, which introduce abstractions for distributed mutable state. We introduced annotations to disambiguate the type of state in the programs, and we also presented a checkpoint-based fault-tolerant model that works even in the presence of mutable state. Thank you very much. I'm happy to take questions.
Hello, Chen Li from Max Planck Institute. I would like to ask you, what's the principle to decide which actually states can be partitioned and which state is partial or which one is global?
Right, so it really depends on the application semantics. So for example, when you think about a case such as the collaborative filtering algorithm that I've shown, the user item matrix, when you look at how it's accessed in the imperative program, it's always accessed by key. You can just go to a user and pick the vector. On contrast, when you access the concurrence, you're actually multiplying. So you need to access all of the state. So in that case, you really cannot partition it because you want to access all. So it's that kind of the reasoning, the line of thought that you need to follow to choose one or the other.
So basically, have you considered like a convergence? It's the, for example, like commutativity of the operations. Do you think that is the major concern when you think about how to annotate the state?
How to allocate the state?
Yeah, about the operation commutativity.
Yeah, so, well, the idea is that when you write the program, it should be already expressing the order in which you want to provide the computations. So if you do a global read, actually the barrier will synchronize, well, it's synchronizing basically the previous computation, right? So if we are not doing, basically what I'm saying is that after a read, the result that you get is consistent. It's just synchronize all the partial running replicas.
Yeah, Chuck, NEC Labs. A quick question. How large are these matrices? How much is the state, mutable state you're talking about?
So for this particular experiment, we run with the Netflix data, and that's like, actually don't remember, but it's like several gigabytes. But we've run other experiments with experimental key value stores running on 200 gigabytes and 250 gigabytes.
Thank you.
Okay, let's thank our speaker again.